Okay, so we're going to take a look at 7.2, which is chemical equations. So I have kind of talked about chemical equations quite a bit, but now I actually have to kind of really, now I'm going to define it so it's a little bit more obvious. So first of all, a chemical equation represents chemical reactions. I also want to say chemical or physical reaction. So I can actually represent a phase change, like ice melting. I can represent that with a chemical reaction. So let's continue. So on the left-hand side, or I should say at the tail end of the arrow, we have what we call the reactants. Reactants are the things that react. Okay, they're the things that we're combining together in order to turn into something else, or just one chemical breaking apart, or one chemical changing phase. So the reactants are the things that are going to be changing somehow. So we represent chemical reactions. We have this little plus sign. The plus sign represents the addition of a chemical. So every time you see a plus sign, it's a division of the two chemicals. See it here, I have magnesium and sulfur. I have two chemicals, two pure substances that are reacting. Okay, you're going to hear other words. You may hear other words. Reactants is the most common one, but you might hear reagents or chemicals or just some version of these things are combining to give. The next thing is this little arrow. So the arrow is actually pretty important. We don't think about it much because it's just an arrow, but this is essentially saying that arrow represents something that says reacts. This is kind of the standard reacts to give. Okay, so that's the kind of verbiage you hear to talk about a reaction happening. So reacts to give, but it's not exclusively, doesn't exclusively have to be reacts to give. You might read a word problem, and a lot of this is like, okay, I can see the reaction, here are my reactants. By the way, here are the products. Products are the result of a reaction. So reactants react to give products. That's the most basic version of it, but chemists use all sorts of different words. So reacts to give is kind of the standard, but you might hear something like oxidizes. Oxidizes, there we go. Oxidizes or combusts or burns. And we can actually have physical changes too, or melts, or boils, or evaporates. So anything that sounds like a chemical or a physical change, that's where your arrow belongs. Okay, so reactants react to give in any of the many words you might hear to give us products. So that is the chemical changes that we're actually seeing. And the other part that's actually missing from this reaction is what I'm going to call, and a lot of people call, phase tags. Okay, a phase tag is something that follows a chemical to tell you what phase it's in. So if I have water, water can come as a gas, water vapor. Water can come as a liquid. And water can also come as a solid if it were ice. So these phase tags we should know well. Solid, liquid, or gas. Every single chemical should come with a phase tag, unless there's some reason why not. Like, oh, everything here is aqueous. I might say something like that. That being said, I just said that word aqueous, and let's talk about what it is. By the way, aqueous. Say it, aqueous. I know aqueous, aqueous, some version of that. So aqueous represents something that is dissolved in water. Water, by the way, cannot be aqueous. Water cannot dissolve itself. But something like sodium chloride, okay, so salt can be dissolved in water. That can be represented as aqueous. Okay, so there we go, salt as aqueous. So again, we're always going to, a proper way to write out a chemical reaction is we are going to have, all right, so if I were to have, let's say, hydrogen react with oxygen to give me water, okay, first of all, this is not correct because I don't have phase tags. So let me zoom in here. So if this is my chemical reaction, hydrogen combines with, by the way, the plus sign might be denoted with some wording like combines with. So hydrogen as a gas combines with oxygen as a gas to give me water as a liquid. So maybe it's making water vapor, okay? Hydrogen, oxygen give us water. There is a problem here, though. I have two hydrogens on this side. On this side, I have two hydrogens. Fantastic. On this side, I have two oxygens. On the other side, I only have one oxygen. So this is not balanced, okay? And we're going to have to be able to balance this, and that's what we're going to do next. But we have to make sure that in addition to having all of the chemicals and the phase tags, we also have them balanced, okay? So we would have to balance this. And I'm going to talk about it momentarily, but we can change the numbers in front, which we call the coefficients. We cannot touch the chemical itself. Okay, so we're going to balance this out, or we can balance this out. We'll balance a bunch, so I'm going to leave this because I think I do this example. The other thing I want to say is if I have NaCl as a solid and I dissolve it in water, NaCl aqueous, okay, so now I have, this has gone through a physical change. It's still sodium chloride, but it's gone from solid to now dissolved in water, aqueous. Okay, so that also represents technically a chemical reaction. That's totally fine. If you have something like, let's say I take sugar, C6H12O6 as a solid, and I write out C6H12O6 as a solid, this cannot happen, okay? I mean, this doesn't represent a chemical reaction. You can write it out, but ultimately what this means is there is no reaction. So we wouldn't really write this out as chemists because there is no reaction occurring. It just doesn't really represent anything. So if you don't have any changes whatsoever, no reaction. We would say, yeah, no reaction occurred. All right, great. So again, reactants react to give products. We add phase tags to make sure. And then the last thing is we need to balance everything out. So once you have your reactants and your products and your arrow in between, you have all your phase tags. The next thing we have to be able to do is balance equations. So equations have to be balanced because of the law of conservation of mass, all right? Law of conservation basically says that atoms are neither created nor destroyed during a chemical reaction. So if they're neither created nor destroyed during a chemical reaction, that means that we need to make sure that we have the equal number on both sides. So we have to have an equal number of hydrogens on one side as we do on the other, equal number of oxygens. So everything has to balance out on the reactants and the product side. There's a couple of little things that I want to point out. The most important thing is, okay, these are the two most important things when you're balancing equations. First of all, never change a subscript when balancing an equation. So if I have water, okay, this right here represents the chemical. Okay. If I needed more oxygen, okay, and I put a 3 there, it is no longer water. Okay, so these subscripts cannot be changed, because once I change a subscript, if I were to put a 3 there, it's now no longer water. It's something else, okay? By the way, there is a subscript here too. It's just not seen. 1 is represented there, okay? In fact, these subscripts can also be called moles. So 2 moles of hydrogen, 1 mole of oxygen make up water, okay? It's an equal ratio of numbers, okay? So in any event, those subscripts cannot be changed. They cannot be changed, okay? So we're going to talk about this later, so I'm just going to erase it for now. But so we can't change those subscripts. But what we can change is we can change this number out front. This represents the coefficient. This also represents moles. So if I were to put a 2 in front here, I'll put a 3 in front. if I were to put a 3 in front here, that represents having 3 moles of water or 3 water. Okay, so looking on a chemical reaction scale, 3 moles of water. Looking on just an individual reaction, this would be 3 water molecules. But either way, it's a count. 3 versus 3 moles is just a counting of these things in any event. So we can change this all we want. Like, oh, actually, I need twice as many. I need 2 more hydrogens. Okay, so I'm going to cross this out and put 4. Okay, so we can have 4 hydrogens there, right? Oh, well, actually, I'm sorry, 8 hydrogens. Oh, actually, we need a 5 coefficient, so I'll put a 5 in front. You can keep changing the coefficient all you want when you're balancing equations. Never change subscripts. Okay. Oh, and then finally, the last little bit here. Use the smallest coefficient possible. We're always going to minimize the coefficient. So if I can divide everything by 5, we're going to divide everything by 5. So you'll see us do that a couple of times. Just always want to use the smallest coefficient. I can't balance it out with, 100 of everything. We're just going to try to make that number as small as possible. So one more time, here's a better representation of it. I have a water molecule changing the coefficient. This you're allowed to do. Changing the subscript, you're not allowed to do that. Okay, so do not do the bottom one there, okay, because you're going to change it. Now it's peroxide. It's something completely different. It's different reactivity. All right. So we are going to, please do this after my example here. How many of each of the following atoms are there in the following molecules? So here I have a water molecule, and I have 2 water molecules. So what I have are 4 total hydrogens and 2 total oxygens present. Okay, because remember, this right here is multiplying these 2 by 2. By 2. So I have 4 total hydrogens and I have 2 total oxygens. Or I could say it differently. I have 2 moles of water and I have 2 moles of water. 2 moles of water molecules. Or I have 4 moles of hydrogen atoms and 2 moles of oxygen atoms. Okay, so we could represent that anyway. The 2 out front represents moles, much like the 2 in the actual chemical represent how many moles for each. Okay, so do these, and we're going to make sure everyone's kind of on the same track in class to make sure that we can determine how many molecules we actually have. So let's talk about balancing the following equations. So I've got a bunch of examples of how to balance chemical equations, and I probably should have added a page in here, so I'm going to add an additional page here. So add page. Okay. All right. So I want to teach you how to balance chemical equations very easily. So sometimes it's really simple. So if I have H2, going back to my example, if I have H2 gas plus O2 gas yields H2O liquid. I want to balance this chemical equation. And the way I teach my students to do it is sometimes it's actually simple. Sometimes you don't need to do it any fancy way. What we're going to do is we're just going to go back and forth between reactants to products until we balance it out. So I have 2 hydrogen on this side. I have 2 hydrogen on this side. And actually, I'll just show you how I would normally do it. Sometimes you don't need to create this, but so I'm going to put all of the chemicals or all of the atoms that I have, or ions if we're doing ions, and we'll change it up when we start doing different reactions. But here we go. So I have on the reactant side, right? This is all reactants. And over here we have products. I have 2 hydrogens and I have 2 oxygens on the reactant side. On the product side, I have 2 hydrogens and 1 oxygen. So what we're going to do, remember, we can only change coefficients. So let's take a look at what we've got. So on the reactant side, I have 2 hydrogens. On the product side, I have 2 hydrogens. Don't need to do anything because we have 2 of each. I have 2 oxygens and I have 1 oxygen on the product side. That means I need more oxygen on this side. In fact, I need a total of 2 oxygens. It's important that we say I don't need 1 more oxygen. What I need is 2 total oxygens. So how do I get 2 total oxygens? Is that a possibility? Well, if I look here, water has 1 oxygen. So if I put a 2 in front, okay, so if I put a 2 in front of H2O, I'm going to change both my hydrogen, and I highly encourage you, if you use this method or when you use this method, to cross out. So I'm going to change by putting a 2 in front of water, I'm changing my hydrogen, and I'm also changing the oxygen. So completely scribble that out so you can't see it. This is going to help you from saying, oh, I have to add to the number that's already there. No, the number is there is no longer valid. Let's recalculate. So now if I focus in just on this side, I have 2 times the 2 hydrogens. So I have a total of 4 hydrogens, and I have 2 oxygen atoms on that side. And now if we look at the equation as a whole, let's start again. So these were balanced, and then I tried for oxygen, which is now balanced, but now the hydrogens are off. So you kind of just keep going back and forth until you balance everything out. So now my hydrogens are unbalanced. I need more on this side. So what do I have to put in front here? So again, I want more hydrogens. So I need, in fact, how many hydrogens do I need? I need 4 hydrogens on this side. So that means that I need to put a 2 in front. That 2 is going to change just the hydrogen. Now I have 4 hydrogens on that side. And now let's check. Hydrogens are balanced. Oxygens are still balanced. This thing checks out. This thing is now balanced. Okay. So the final result is 2 hydrogens. The final result is 2 hydrogens, 1 oxygen molecule, and to yield to give 2 water molecules. So this thing is balanced out. Okay, good. All right, so let's try something else. Let's give, this is a combustion reaction, which we're going to do later, or combustion reactions, which we will do later. C5H12O2. And this is a gas, let's say, plus this is a gas, is going to give me CO2 gas and water as a gas. Again, the only thing I'm allowed to change are coefficients. Give myself much room over here. This plus, there we go. Okay, so we're only allowed to change coefficients. So again, I am going to put these things in order. Carbon, hydrogen, and oxygen. By the way, the thing you choose to do last, I always choose something that's kind of by itself. Because if I ever put a coefficient in front of oxygen, I only change oxygen. That means if I have both of these balanced, that means that I can do oxygen kind of on its own. So always choose something that's kind of on its own without any pure element is kind of what you want to choose to do last. It'll always work out best for you. Okay, so let's take a look. So right now, I have just 5 carbons, 12 hydrogens, and 2 oxygens. So that's easy enough. So 5 carbons, 12 hydrogens, and 2 oxygens. On the right-hand side, I've got 1 carbon. I have 2 hydrogens. And I have, oops, there we go. I have 3 oxygen. Make sure you look for all the chemicals to see if you have more than 1. I have 3 oxygen. It seems like nothing is matched. Totally fine. We're just going to start. So we're going to start with the top. We're going to balance carbons. I need more carbon on this side. In fact, I need a total of 5 carbons, if possible, on that side. So here we go. I have CO2. If I put a 5 in front, that means I'm going to have 5 carbons. So let's put a 5 in front. So by changing the coefficient in front of CO2, it is going to change my carbon and my oxygen count. So I'm going to get rid of those, and now I'm going to recalculate. So I have 5 carbons, and now I have 10 oxygens plus the 1 oxygen here gives me a total of 11 oxygens. Again, we don't care what that number is until we get there. We just want to keep track of it. Next up, I have 12 hydrogens on the left, two hydrogens on the right. I need more hydrogens on this side. In order to get 12, I need to put a 6 in front. A 6 is going to essentially give me 12 hydrogens, is what I'm looking for. Because I put a 6 in front of H2O, I'm changing the hydrogens. I'm also changing the oxygens. So let's do a quick number count here. So I have 12 hydrogens, right? So 6 times 2 is 12. And then I have, 10 oxygens here. 10 oxygen. And over here, I have 6 oxygen. So for a total of 16 oxygen on that side. Okay, so 16 oxygen total. So carbon, we're going to just check and make sure that we're still balanced. 5 carbons, 12 hydrogens, and now the only thing left to balance is my oxygen. So I have 16 oxygen here. I have 2 on this side, which means this one needs to go up. I need 16 oxygens on that side. What can I put in front of O2 in order to get 16 oxygens? Well, 8 times 2 is going to give me 16. So I changed oxygens. 8 times 2 gives me a total of 16 oxygens. Let's check again. 5 carbons, 12 hydrogens, 16 oxygens. This checks out. It is balanced. There we go. So we've balanced it. That's essentially how we do it. Again, some things are going to be easier than others, but this is what we've got. Okay, so this is kind of how we have to balance things out. We just kind of go back and forth until we balance it out. So let's do one other one. This one's going to be a relatively easy one to do, I hope. Plus O2 yields Fe2O3. So this is rust is a solid, oxygen is a gas, and iron is a solid. Again, we are only changing coefficients. So I want to balance oxygen, and I am putting iron second. So the last little bit of this, I am going to put iron second because there is 1 iron. It means I can add any number here, and I'm going to be able to balance out the iron. I don't have to worry about the 2 or the multiple. So just trust me on this. Always go for anything. If I have 2 things that are isolated, go with the thing that only has 1 of it. It's going to make your life a little bit easier. So here we go. So why don't you pause this and try to balance it out, and then I'll walk through it. Okay. 2 oxygens on this side, 1 iron. On the other side, I have 3 oxygens and 2 irons. So let's balance the oxygens first. So here we're in a situation where if I put a number in front of this oxygen, watch what happens. All right, so let's just put a 2 in front. That's going to change this to 4 oxygens. Wow, okay, so now are we balanced? No, we're not balanced yet. So I need more oxygen on this side. Fine, let's put a 2 in front here. That's going to change both the iron and the oxygen. So I now have I now have 6 oxygen and I have 4 iron. Okay, let's check. Are we balanced? No, we're not balancing. Again, we can change the coefficient as much as we want. I need more oxygen on this side. In fact, I need 2 more, or really what I need is 6 total. So what I'm going to do is I'm going to say, all right, well, I need 6 total. So let's change this to a 3. That's going to change the oxygen again. I now have 6 oxygen on this side, and it doesn't change anything else. Oxygens are balanced. Fantastic. Now I have irons to balance. I need more irons on this side. So let's put a 4 in front. That changes my oxygen count or iron count. Now I have 4, and now everything checks out. Again, sometimes you might need to change the coefficient a couple of times, and we just do. Okay. All right, great. So balance the following equations. So notice that all of these, I'm just going to ask you to balance. They're relatively simple. We'll talk about this one in class. This one is important. This one is important. We're going to learn how to balance those things. a little bit simpler. In fact, I can tell you right now, you should give these a try. But when you're balancing these, which one do you want to do last? We should do iron last because it's isolated over here. Okay. And if we look at what we have here, notice that we have hydrogen. Sure, we've got hydrogen, but we also have SO4 2-. So instead of balancing sulfur and oxygen separately, I know that sulfate always remains. I know that sulfate always stays together. So I can act like it's an atom. So whenever you see a polyatomic, you can kind of set that aside and kind of do it on its own. And in fact, down here, I've got phosphate and I've got OH, which actually water is just H and OH together. So we can usually balance those separately. Okay, so just recognize when you have a polyatomic, you can kind of add it to that list this way. All right, but we'll get there. All right, so hydrogen reacts with chlorine to make hydrogen monochloride. So this is, again, where naming is going to be important and knowing about chemicals becomes important. So I'm going to walk you through this. So hydrogen, how does hydrogen typically come as a chemical? Hydrogen comes as one of the many that comes as a diatomic. Okay, so a lot of gases come as diatomics. In fact, they come as H2 and hydrogen's a gas. Chlorine doesn't come as just chlorine. Chlorine also comes as a diatomic gas. And hydrogen monochloride, HCl, and we don't see anything about what it is. So honestly, the phase does not matter as much there. Gas is usually what you would put. So hydrogen plus chlorine yields HCl. Go ahead, balance this out. Should be relatively simple. So with that in mind, for the next one, chlorine, we know it's a gas. By the way, all halogens come as gases. In fact, oxygen, nitrogen, fluorine, chlorine, bromine, iodine, they all come as diatoms, and hydrogen is the other diatom. So that's the list of things that come as diatoms. Notice it's that kind of that corner in the upper right. So chlorine reacts with, oh, hold on, what's the phase? That's right, it's a gas, reacts with carbon. Carbon typically comes as a solid to give me carbon tetrachloride. Again, it doesn't really give me a list. I know CCl4 is a liquid. And there we go. So go ahead and balance that one. The next one, hydrogen as a gas, reacts with oxygen as a gas to give me dihydrogen monoxide, so water. And we're going to say that this is a gas as well. All right, so the rest of these, don't worry about the phase tags, but why don't you give balancing these a try, and we're going to try them in class. Okay, in fact, these as well. Okay, good. So that's pretty much it for balancing chemical equations. We're going to do a bunch of these examples in class, and from that, I will put up a video next of classifying different types of reactions.